Hello everybody, welcome to another problem session. So today we're going to do a couple of different ways. A very standard problem we have done before. So we usually don't say it at live frame and CM frame, but we're going to use those words. So here is a frame, we're going to call it a live frame, in which one of the particles initially is at rest. So this is a live frame. And live frame is the frame in which, say, particle number 2, this is number 2, which is M2, is at rest. So in this frame, before collision, so this situation before, so this is at rest, and we're going to use it, say, Y1, X1. So this is frame number 1. So this is frame 1. So in this frame, it's at rest, but another mass M1 is moving this way with some speed V1. And this speed is respect to this, so I'm going to attach another letter there. Okay, so this is a live frame, and this before. And after, we'll say these particles get stuck. So the particle, I'm gonna say this is the net particle, and this particle is gonna go with a speed, I'm gonna call it U, and this particle has a mass M. So we want to address this both in non-relativistic and relativistic way, the standard way. So the standard way is to a couple of questions. Questions would be, what is given M1, M2, V1, kind of V11. And so this is U is in frame 1, right? This is frame 1. So U of M in frame 1. Given this, so given this, what is U? This U. Okay, so that's one question. And that's very standard question. Okay, so to answer this question, you have a couple of different ways. Okay, another question would be, what is value of M? If M1, M2, V11 are given. Okay, so let's work this out. Okay, both of these. So let's see if I were to do non-relativistically, like the old ways, non-relativistically. What we're going to do? Well, momentum conservation along the x-axis. So we have M1, V1. I'm just going to just have 1. I'm going to just write 1. Okay, we're going to do live frame, and then we're going to do center of mass frame, and that we're going to call it U. I mean, just a frame will be used 2 for that. But so far, it's just the x component of the momentum plus 0 equals to this M. And in the non-relativistic case, we have M1 plus M2 is M. In non-relativistic, you have mass conservation. Okay, so we have this plus m times u, and you can just solve it. U equals to m1 over m times v1. So that's the answer that you get, right? We can do energy conservation. So this we have a half m1 v1 square. We don't use rest energy in non-relativistic case. Plus 0 is equal to, when you go here, this is going to be half big M u square. Okay, so this doesn't give new information here, because if you use this, then you plug in there, you can see that. Let's plug in. So this is this can be, it's consistent. These two should be consistent, right? So 1 over 2 cancel out, and so we have a 1 over m1 v1 square equals to, you have a 1 over mu square, and from this guy we cancel out from m1 v1 with m2 vu, and then we have, if this was all the case, then you have a m equals to m1, which is not correct, right? So there's something missing here, and what's missing here is binding energy. So whatever is missing is binding energy. So m is actually m1 plus m2. So if you were to write this down, now it's consistent. Okay, you'll have m1 v1 square 1 over m1, and the other side will be m1 plus m, or 1 over mu square. And so this we write down in terms of m1 v1 square. So this is 1 over plus binding energy. So you will have a 1 over m1 v1 square plus binding energy. So binding energy will be simply, now we have to carry 2 because we can't cancel 2 here. So noticed. So bring it on the other side. So you have m1 v1 square 1 over 2 m1 minus 1 over big M, and you can further simplify it, because it's going to be half m1 square v1 square, and you have m1 big M, and so big M minus m1, and this becomes m2. So just you get half m1 v1 square times m2 over m1 times m1 plus m2. This m1 cancels out. So you see that this is just an energy of the first particle. So this is m2 over m1 plus m2. So this is the binding energy that has to be present for it to make have a consistent. So you just can't just say kinetic energy equal to that. That would be wrong. That will be wrong. So you actually need binding energy to make sense of this, assuming this is the case, right? Now we don't assume this in when we go to relativity, and these things will be kind of greatly modified. Okay. So this problem is in relativistic way would be the same principle. We will still have a momentum conservation. right? And energy conservation. But the whole thing will work out quite differently. So when you have momentum conservation, we can try to address this question: how do you find out what the value of u will be? Okay, so we are just in one frame, so we use the same simpler notation. Okay, and these will be now particle 1, but its rest mass, and particle 2 is rest mass, and this is its rest mass. So this will be rest masses now. So momentum conservation will be momentum of this will be non-zero, momentum of this will be 0. So momentum of this will be so it will be gamma v1 m10 v1. So this is the p momentum, x momentum for particle 1, and the other one is 0 because it's at rest. It's v is 0. This part is not 0 and this is 0, so it gets you 0. And other side we have a gamma of u m0 u. So we want to solve this for u. That's one of the questions, right? So how do we solve this for u? Well, put the m0 on the other side. So we have a u over square root of 1 minus u square over c square equals to gamma of v1 m1 v1 over m0. Okay, so we could have further simplified the notation that all the m's will be rest masses. Okay, so if you like a much simpler notation, you can say, hey, m1 will be rest mass, m will be rest mass, but I want to just put 0 there, so it's not really fully simplified yet. I want to solve for u. So one way to do it is square it and get rid of this, and then square this. So that right side, let's call it some kind of quantity a. So this whole thing is some a. So now cross multiply, you have a let's also call divide by c square. So 1 over c square, 1 over c square. So that's what we're going to call a, and let's call a known quantity x is u over c. So so this thing becomes x square over 1 minus x square equals to a, and so this will be x square equals to a minus ax square. So 1 plus a, x square is a, and so x square is a over 1 plus a. This is pretty complicated, you can see already. So x, and we're just looking for the magnitude, will be square root of just plus here, a over 1 plus a, and so u equals to c times square root of a over 1 plus a. Okay, you can already see this whole thing can be very complicated, but we solved it. Okay, you can see we solved it. It's numerical value, you can get numerical value. Now, other questions: what the value of m or m0 if it was from the other things? Now that turns out to be a pretty interesting problem. If u is not known, we can definitely, you know, this will all be in terms of m0. M0 will be there, so you can't just say plug this in here and get it from one equation and get two unknowns. No, you can't get this using this, so we'll have to do it a little bit differently to get m0. So to get m0, we can this is the whole momentum, right? So we need to find energy in a little different way. Okay, so we're going to do energy conservation, but I'm going to do it even this one I'm going to write most. You can see already very complicated way I've done here. It's really not necessary to do it. I can do it much more compact way. So I'm going to write this like I'm going to write this P1 and write this guy as P. Okay, so this says P equals to P1. Okay, so if P equals P1, so for the composite particle, so I'm going to look at the composite particle. I'm going to say its momentum is momentum P1, and I'm going to use for any particle in relativity, energy square equals to P square C square minus m naught square C to the power 4. So this is the case for every particle, momentum energy related. Okay, so from here I would get P equals P1, and so you can see I can, if I write P square would be P1 square, and P1 square can be P1, so P square, let's call it C square, so that will be C square P1 square, and I can replace this using energy for the first particle is this relativistic energy plus m0 square C to the power 4, right? So this will be one equation which we can use, and that's for the composite. This for composite. Okay, and then I can write energy for the composite. So energy for the composite from energy conservation, whatever the energy it has must be equal to the energy that these people have. And how much energy this has? So it has E1 plus M20 C square. It's the rest energy of this guy. So I really don't include, this includes all the binding and all kinds of stuff. The binding energy in relativity will be, so we had M1 plus M2, now we have M0. So M1 0 C square plus M20 C square minus M0 C square. So this will be the binding energy. Okay, so and you know, so this is the rest energy. Anything above the rest energy it should have been binding energy. So that's the way binding energy is defined. So now here, now these two guys must be related like that to the so this is the property of this particle. So I just use in here. So if I square it, you have E1 plus M20 C square from here, and equals to this is a E1 square plus M0 square C to the power 4. So if I minus, this is actually this should be plus, this should be plus, this is a plus. I made a mistake here. This is a plus, so I used it here. It should be a minus here. So this is minus here, and so this is m0 square c to the power 4. Okay, to simplify, I'm gonna have m0 square c to the power 4, and even square will cancel out. I will get m10 square. This m10 square is m10 square. So m10 square when this goes on the other side, it should become minus m10 square c square, and then you have a plus m20 square c square, and c to the power 4. I'm making a lot of tiny mistakes here because I'm skipping steps, and then you have minus 2 times m20 c square e1. I just noticed more mistakes here. This actually is a plus here because this coming from this guy in here. Let me so this is plus here, so that's why these minus signs don't make sense to me. And then from here this was minus and this is plus. So when I expand this and I bring this again, this becomes a plus, and these guys all plus. Yeah, now it's right. So m0 now is going to be, you can see c to the power 4, you can go out and cancel c to the power 4, 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 you can cancel, and this becomes just c squared like that. And so m0 will be square root of that, and just m0 will be just a square root of this. So much more complicated expression than what we got earlier. If you go back and look at it, this at small speed it should become non-relativistic. So you can just check at small speed when v1 is much less speed of light, then epsilon1 will be over c squared, just m1 and m10. So if you do it over here, that turns into a square root of m1 plus m2 square, and that just turns into m1 plus m2. So when the speed is of the particle is much the speed of light, then the composite particle's mass is just the sum of the mass of the two particles. Otherwise, you have a pretty complicated expression. Okay, so this just we did in one frame. Actually, all of these calculations can be done really not just in the lab frame, but we can pick a frame in which this thing is at rest, and that frame will be center of mass frame. Okay, so let's look at the same problem in the CM frame. So this is like center of mass frame. In non-relativistic, we call it CM is center of mass. And this, but this is really better to think of it as center of momentum. And then you can have in both system, okay, both non-relativistic and relativistic. So let's look at a non-relativistic. So what we have is this is the original lab frame. The particle 1 comes and particle 2 is at rest. Here this is velocity with respect to this frame. The second frame is defined so that this is at rest, not this was at rest in the left frame. So we choose the frame where particle 2 was at rest. If particle 2 was moving, we move to a frame in which particle 2 is at rest and give the relative velocity to particle 1, extra relative velocity to the particle 1. Okay. Now, in this frame, what will this look like? This will look like, now, if the frame is moving, then this guy is going to moving to the left, and this guy will, depending on this guy will still be moving to the right. Now, in such a manner, the total momentum, if you momentum conservation will mean this velocity has to be different than that. I'm going to call it v1, but let's call it u's, u1, u2. In this we had call it v1 and v2 equal to 0, and okay, so we can call it u1, u2 in the center mass frame. Okay, so in non-relativistic, momentum conservation will give me, so in this frame, momentum conservation will give me momentum here equal to momentum there. So actually this has a momentum of 1 equal to momentum 2, momentum of 1 plus momentum of 2 equal to 0. That means P1 equals minus P2. So that's one equation. And when you do this out, you have M10 U1, and if this is the arrow and this is all positive, then this will be equal to M20 U2. So this one thing I write immediately. You want to find what U is, then you have to go back there and you can see what U1 looks like and what U2 looks like, and from there you can find out. So you have to kind of go there to find what the relation between U1 and U2 is. So the U1, so you can see that U2 equals to U. This U2 has the same value as U, and U1 is equal to V1 minus U. So now if you plug in there, you can get M10 V1 minus M10 U equal to M20 U, and when you transfer this on the other side, U equals to M10 over M10 plus M20 V1. So same as before, but I had to kind of some of the information has to go back and forth. Okay, so this is non-relativistic. We can try to do the same kind of thing in the relativistic and see what happens. Okay, let's do in relativistic over here. I was gonna erase it and then let me get a different color. So let's do a relativistic. Okay, so we're still gonna have the same thing, momentum conservation. So one equation will be P1 plus P2, so P1 and P2 in this frame 2, in frame 2 equal to, again, frame 2, this is P of this guy, which will be 0, P of big mass in frame 2, and that's equal to 0. So that will just P1 in frame 2 equals to minus P2 frame 2, and we can write over C that in terms of magnitude, P1 in 2 equals to P1, P2 and 2. So or we can P1 2 square, C square will P2 square, C square, and that's one way to we will use later. Okay, so this can further be written down as energy of first particle square minus first particle square c to the power 4 equal energy of the second particle square minus is rest mass c to the power 4, and then we can actually write down E1 square minus E2 square equals M1 0 square minus M2 0 square c to the power 4. So we are going to call this equation 1. And another one we would need is energy conservation. So you have energy 1 plus energy 2. Energy 1 plus energy must be energy of this final, of this energy. And this is the net energy. So this would be, we will say it is at rest. It is rest mass m0 c square. Now 1, this is equation number 2, but the 1 can also be written as E1 minus E2 equals to this whole thing, so right hand side divided by E1 plus E2, and I can use this to actually simplify that. So it's going to be E1 minus E2 is equal to M1 0 square minus M2 0 square C square over M0. So this units are all right. So we're going to call this 1 prime. Using 1 prime and 1, so from 1 prime and 1 and this 2, you add, you can get E1, and you divide, you're going to subtract, you're going to get 2. So E1 was just going to be 2 times M0 M0 square plus M1 0 square minus M2 0 square, the whole thing C square. And similarly you can get E2 is equal to M0 square plus M2 0 square minus M1 0 square over 2 M0 C square. So so how do we get this U? That's the question, right? We've got the U like this. How do you get the value of U? Well, we have to again connect into these two. So this U2 here come from this being 0 here, and so this U2 is actually same as U, you know. So this U2, so if you look at a momentum and energy, so if you look at a P2 is going to be just gamma U corresponding to U and mass 20 U. So magnitude of P2 is this, and from these two we should be able to get what the U will be, right? Okay, let me erase that and see. I'll show you some steps. So if I know energy of a particle and momentum of the particle, I can get speed of the particle very easily. So this generally, suppose energy and you know P, so energy is gamma, whatever the speed is, and m0 c square, and momentum is gamma m0, the speed of that particle. So if you take a ratio, P over E is simply V over c square. So V is c square P over E, right? C square P over E. So if this is the P, so in this case it will just simply be U. This will simply be V is U equal to C square gamma U M20 U, and this whole thing is equal to, so let's call it delta M, let's call it mu c square. So this whole thing is mu and this c square. So this is mu c square. Cancel out, cancel U out. So mu equals to gamma U M20. So 1 over gamma U is M20 over mu, and this stuff is simply a square root of 1 minus U square over C square, and then solve for U. So whenever you have energy and momentum figured out in a relativistic situation, you can always get the speed. Okay. All right. I think I'm going to stop here. This is a couple of things to notice. Relativistic and non-relativistic formulas work out quite differently, number one. And number two, if you don't have to do relativistic, you shouldn't do it, because it's so much algebra, so much more algebra. It's just not worth it. So the first thing to figure out is your problem not going to be non-relativistic or not. So in your problem, if the speed is much less than c, then just go with the non-relativistic. It will save you a lot of pain. But if v is like 1/10 of a c or more, then you have to you're forced into doing. Now you're in the situation where it's observable, and you shouldn't just do out non-relativistic. You may do out non-relativistic to get a sense of things. You might even get some interesting information, but it's really will be very important to actually work out, even if it costs a lot of algebraic steps. And it's very easy to make a mistake. When we do the algebra, you have to do it twice or 3 times, make sure you got the same answer. And you can see, I've been seasoned at this, and still I kind of was too fast, and I got some signs. When you're copying a recording, it's hard to not make a mistake, and it's hard to correct those mistakes. Anyway, so that's it. If you like this kind of explanation, please hit the like button. You can check out my website, and you can also subscribe to the channel. See you in another video. Bye.